Hi, everyone, and thank you for listening and watching my talk. My name is Manuel Buen-Abad. I want to tell you a little bit about a project that I did with postdocs Raymond Ko and Keisuke Harigaya. Here is the archive number of our paper, which is titled Common Origin of Warm Dark Matter and Dark Radiation. I want to start by thanking the organizers of Cosmology from Home. This is such a great opportunity, particularly in these times, and so I am very grateful to be part of this. Let me start by giving you an outline of my talk, first, the motivation behind our project, and the model that consider in our project, some results from fitting to the data, and finally, an outlook and conclusions. So first of all, the motivation. Precision cosmology, I hope I don't have to convince you, has achieved such a tremendous and beautiful accuracy and exquisite precision. It comes to mind, for example, the Planck satellite, who has given us a tremendous wealth of data about the cosmic microwave background. Another one is the Galaxy Survey, the SDSS. Here's a 3D map of our universe that gives you information about the matter structure, matter power spectrum. And from all this wealth of information, one winner has risen as the standard framework, the standard model of cosmology to explain all of this data, and that is LambdaCDM. Its name, as its name suggests, lambda is a cosmological constant. It's a kind of dark energy. CDM is a cold dark matter because it demands 80% of dark matter to be cold dark matter, collisionless and without interactions. And this very simple framework does an amazing job at fitting and explaining the data. Really, really good. However, there seem to be a few cracks appearing in the face of LambdaCDM. On the experimental side, there are the well-known tensions such as the H0 crisis, H0 tension, in which the direct measurements of the Hubble H0 parameter, the Hubble expansion parameter, turn out to be bigger or larger than the deduced value from indirect measurements of the same. That is to say, for fits of LambdaCDM to Planck data. From some reviews to look at these papers. On the other hand, there's also a milder, however non-negligible tension in sigma 8. Sigma 8 is the parameter that tells you how the size of the amplitudes of the fluctuations at scales of 8 megaparsecs in matter. That is to say, it tells you how close there is matter at these scales. It turns out that the direct measurements of sigma 8 are smaller than the value deduced from fitting LambdaCDM to Planck data. And you can look at some recent results over here. So that's on the experimental side, something that not everything is all right in cosmology and LambdaCDM. There's also theoretical motivations, among them being that LambdaCDM was never meant to be the final word, right? In particular, it doesn't tell you anything about the origin of dark matter, right? And that is an interesting theoretical question, and usually one that gives rise to very rich dark sectors, very rich phenomenology and cosmology. On the other hand, there's also particle physics problems that one would think have nothing to do with dark matter, with cosmology, that end up giving you dark matter and interesting cosmology as a byproduct. For example, the hierarchy problem that with SUSY and supersymmetry and giving you WIMPs, or the strong CP problem giving you actions, which is a candidate for dark matter as well. Neutrino masses giving you stellar neutrinos. All of these things have effects on cosmology. So from these two experimental and theoretical motivations, we want to look forward a little bit ahead of LambdaCDM, beyond LambdaCDM. So people tend to look in different places. One of them is dark sectors, what I like to call dark paths to go beyond LambdaCDM. And these dark sectors are dark matter, for example, that should be part of it, but also could include things like dark radiation, extra radiation components, or dark energy added to the mix. And these dark sectors would have a veritable zoo of particles and interactions and all these things that would have interesting consequences on cosmology. I want to narrow down on two of these most common dark paths beyond LambdaCDM, the dark path of dark radiation and that of warm dark matter. So dark radiation, as its name suggests, is an extra amount of radiation beyond photons and neutrinos. It can be parameterized by delta N effective, which tells you the extra effective or equivalent amount of number of neutrino families that are in this dark radiation. And its energy density is given by this. Don't worry about these prefactors. It scales like delta N effective and this temperature to the fourth. Now, the effects of dark radiation on the cosmology are very well understood. For example, the CMB peaks get shifted. The silk damping gets increased. Admit radiation changes the time of radiation matter equality. Of course, that time is well fixed. So that means that you need to increase dark matter. the amount of matter in the universe, and that in order to keep matter radiation equality, which means that at the end of the day, very indirectly, dark radiation ends up increasing the structure, increasing sigma 8, and by the way, making sigma 8 tension worse. So this is a very interesting correlation between dark radiation and matter, right? Like delta N effective is correlated, positively correlated with sigma 8 in this naive dark radiation path. There's also the other path of warm dark matter, in which a fraction f of dark matter is warm, that is to say it has a non-negligible temperature or velocity. As such, it free streams around in the universe, and you can characterize it free streaming by a free streaming length that is proportional to the time of A and R, the scale factor at which the dark matter becomes non-relativistic, or inversely proportional to the temperature of the thermal bath at that same time. What this means is that all the modes that are smaller than this scale that enter the horizon before the A and R get washed out, get suppressed by the free streaming of the warm dark matter. So this is a crash course, your crash course on dark radiation and warm dark matter. And these are some of the paths beyond LambdaCDM, the dark paths. So in our model, we put them together, and the results are rather interesting, if I may say so myself. So let me tell you now about our model. Our model is in our name, which is rolls off the tongue. It's common origin of warm and relativistic decay particles. Common origin of warm and relativistic decay particles, or by its initials, coward. So our coward model is very simple. You have a particle chi1 that decays to a particle chi2, which is massive, and phi, which is massless or very relativistic. So indeed, you have a chi1, therefore, that is a decaying dark matter, an unstable massive parent, who is parameterized by its energy density ρ1 and its decay rate gamma, or if you prefer the scale factor at which it decays. Then it decays to a particle chi2, who is also massive. It's a stable daughter, but its mass is smaller than the mass of chi1, which means that during the decay, it comes out with a boost. It comes out relativistic. Eventually, its momentum redshifts away, and at a time A and R, it becomes non-relativistic and starts acting like matter, but like warm dark matter. And you can parameterize chi2 as well with this A and R, and a fraction of dark matter today that is in these chi2s. And finally, the last decay product, the daughter, the lightest massless daughter, phi, that acts like dark radiation. It can be parameterized by delta N effective, as we have learned. So therefore, our Coward model has all these 5 parameters. 2 for chi1, its abundance and its time of decay. 2 for chi2, its abundance and its time when it becomes non-relativistic, and delta N effective, which is the abundance for the relativistic component. Okay, very simple. Decaying dark matter. So let me tell you a little bit about the thermal history. The x-axis I have the scale factor, and the y-axis I have the abundance. And here's the thermal bath in red. This is the standard model temperature, standard model bath. Rho1 here is the energy density in chi1, the parent particle, which scales like matter all the way down to A decay, the time at which it decays and it goes away. Then Rho2 and Rho phi are the energy densities in phi particles and chi2 particles, and they are growing compared to Rho1, at which point they take over it once Rho1 goes away. And notice though that since they are light with respect to chi1, they end up being first like radiation. They have the same abundance and they scale down like radiation. Down until some point A and R, from which phi continues scaling like radiation, but chi2 scales like matter, warm dark matter. This time A and R becomes non-relativistic. So this is the rundown of the thermal history of the Coward model. Now note, however, that from this thermal history that we can determine that some of these parameters are unnecessary. Particularly, for example, from the common origin at a decay of the warm dark matter and the dark radiation, we realize that you can express the initial abundance of chi1 particles in terms of delta N effective, right? Because the abundance of phi and Rho2 are actually related to delta N effective, and that comes from the decay. So actually I can solve Rho1 in terms of delta N effective, right? I don't need this parameter. It is not a free parameter of the model. Furthermore, during this entire time, phi and chi2 are like radiation, at which point non-relativistic chi2 becomes like warm dark matter and ends up with an abundance given by F. So by comparing the abundance at A and R, which is given by delta N effective, and the abundance today of chi2, which is given by F, I can solve where A and R happen. So I don't need A and R. I only need to know F and delta N. Once again, A and R is not a free parameter of the model. So at the end of the day, I have only 3 parameters. In our Kawa model, there's only the time of decay, the abundance of the dark matter, the fractional abundance of the warm dark matter, and the delta N effect, the amount of dark radiation. And A and R, I don't have time to derive the expression for you, but A and R is then given by this expression, proportional to this expression. Notice that is proportional to the delta N effective. Or if you prefer, to parameterize in terms of the temperature of the thermal bath at this time in which the chi2 becomes non-relativistic, you can find that it's inversely proportional to A and R and end up with the following expression. Noticing that if F and delta N effective over the same order of magnitude, then the temperature of the thermal bath at which it becomes non-relativistic, it's about 5 electron volts, that is to say, about an order of magnitude above the CMB. So this is interesting. Once again, you have 3 parameters for our model and this interesting relationship here. So let me take that into account again. So you have this temperature and at which things become non-relativistic, I2, in terms of F and delta N. That is within the system of the Coward model. But more generally, warm dark matter has this expression for the free streaming length, right? Do you remember I mentioned this about, and it depends as an inversely proportional to the temperature at which the warm dark matter becomes non-relativistic. So I can put these 2 guys together and end up with the following heuristic expression. The free streaming length of the warm dark matter is proportional to this expression. Notice that the free streaming length is proportional to the amount of dark radiation. That is to say, the more dark radiation I have, the larger the free streaming length, and therefore the more modes end up being suppressed in the matter power spectrum. That is, sigma A, which tells you how much structure you have, how much matter power spectrum you have, and delta N are anti-correlated in the Coward model. You increase delta N, that means you increase lambda FS on the free streaming, and that means that you have more suppression or smaller sigma N. This is the opposite that when you would naively expect from just having dark radiation from a naive dark path extension to LambdaCDM, but you have an extra component of dark radiation. Dark radiation gets increased, you need to increase matter to keep matter radiation equality, which means that you increase sigma N. In the Coward model, that does not happen. The exact opposite happens. So this is very interesting. This is the main takeaway from this section, if I may say so. Again, within the Coward model, sigma 8 and delta N effective are anti-correlated because of this common origin of the dark radiation that you have and the warm dark matter. So this is the one slide about particle physics that I'm going to mention. This is an interesting model. Does it get realized in phenomenology, in particle physics? The answer is yes. In well-motivated models, you can ask to have supersymmetry and axions. If you want to solve the strong CP problem, and if you have axions in supersymmetry, you will have an axino, a superpartner for the axion, and this axino could decay to gravitino and axion, or if the gravitino is heavier, gravitino could decay to axino and axion. So here, whoever is the heaviest will be chi1, the other one will be chi2, which is lighter but not massless, and the axion whose mass is very, very small would be the phi particle, right? So that means that you have all these particle physics parameters, the mass of the light, the heaviest, the lightest, and then the initial abundance, and you can map these particle physics parameters into cosmological parameters that I've been telling you about. So that's a realization of a cowardly behavior in cosmology from BSM. That's all the particle physics. So that's it. This is the model. Again, common origin of warm dark matter, dark radiation with interesting correlations between sigma 8 and delta N effective. So we embed this into a Boltzmann solver, a class, code class that allows you to solve the evolution of the universe. And then we run MCMC with MontyPython to scan over the parameters. Now, we noted that if the time at which chi1 decays is very early, happens very early in the universe, then it has no effect on the field, right? Basically, all the wave numbers, all the modes that enter the horizon that are observed, and they're after a decay, so they have no effect. They do not get affected by the time of decay. So just to make our lives easier, we assumed in this Monte Carlo run that chi1 had already decayed. We just fixed the a decay at 10⁻⁷. We noticed and we made sure that changing that doesn't fit, changing our fits. So essentially, within the Coward model, we're only fitting to two parameters: the amount of direct radiation and the amount of dark matter, of warm dark matter. But they are related from their common origin. That's the interesting thing. This is not just dark radiation and warm dark matter. These are related. This is the Coward model. So that's how we implemented this in numerical code. We then fit it to data, CMB Planck 2018, temperature and polarization, as well as lensing, and the BAO data. And we do not fit, that's it. We do not fit to sigma 8 data, not fit to structured matter parts, structured data. We just let this see what happens with Planck data. And these are our results. Here you can see our numerical results, two-dimensional contours, 68 and 95% contours for sigma 8 and delta N effective. In gray is LambdaCDM, just good old vanilla LambdaCDM. In blue is LambdaCDM plus dark radiation, in delta N effective. And in red is our Coward model. And you can immediately see what I have been telling you about. In blue here, this blue arrow tells you that in the usual vanilla naive extension to LambdaCDM, would you have dark radiation, delta N effective and sigma 8 are positively correlated. They are correlated. You increase delta N effective, you increase sigma 8. Again, because you need to keep matter radiation equality, because it's very well measured, and that means you need more matter, which means you have a larger sigma 8. That's what happens. In our Coward model, though, they are anti-correlated and very widely so, right? Small change in delta N effective, you get smaller sigma 8. And the reason is because this common origin between the dark radiation and the warm dark matter has given rise to this expression for the free streaming length, right? That is proportional to the delta N effective. The more dark radiation you have, the larger the free streaming length, the more structure you wiped out, and the smaller sigma 8. So that's in our Coward model. You can see it very clearly here in our results from MCMC. Here are some other two-dimensional contours that you might find interesting. May I draw your attention to this quadrant over here, sigma 8 versus omega m. Here is LambdaCDM in gray and blue, LambdaCDM plus dark radiation, and in red, our Coward model. You can see how it naturally extends to lower values of sigma 8 again, and such that it can address the sigma 8 tension. Here in green is a band from CFH lens measurements, and we could add kids and we could add any other measurement, but here it is for CFH lens. Note again, we're not fitting to CFH lens. We're not fitting to kids. We're not fitting to any measurements of sigma 8. This is something that comes out naturally from the Coward model just by fitting to Planck. And the improvement over the fit of LambdaCDM is a very, very moderate. It's a -2. It does not degrade the CMB fit, but it allows for an easing of the tension in sigma 8 very naturally from our model. So finally, some outlook and conclusions. So an outlook, something to look forward to. Remember that CMB stage 4 is going to probe delta N effectives to orders of 0.03. That means that within the context of our Coward model, remember we have this anti-correlation. We have a prediction for what sigma 8 ought to be. If you see a positive detection of delta N effective 0.03 or whatever, Coward model predicts a correlated or perhaps anti-correlated signal. It should say, oh, you saw delta N effective, you should see a suppression in sigma 8 of this much. So that's interesting. You can rule down this model just like that. And maybe another outlook point is beyond future work within the context of our developing our model. Just remember that we fixed a decay, time of decay, and we'd like to make a full implementation of this, solve the phase space distribution function for all the particles. That's all very interesting. Look for something to look forward to if you like to follow up on this story. And finally, some conclusions. I would like to divide them into two, particular and general conclusions. Particular regards to Coward. It's a theoretically well-motivated model, supersymmetry and actions. It solves the sigma 8 tension without degrading the CMB fit and without asking it to solve the sigma 8 tension. It comes naturally. I did not feed to the sigma 8 data. Also, a Coward model combines two very common avenues for beyond LambdaCDM, dark radiation and warm dark matter, with very interesting resulting effects, which in fact counterintuitive, more dark radiation, suppression of matter power spectrum, and with few parameters, because all of these relationships that happen between them, as I told you from the thermal history. And finally, And perhaps the most important conclusion that I want to draw is the moral of the story. This is not related just to Kawa, but just in general. This is that what you would think naive extensions to LambdaCDM in dark sectors or whatever, naive extensions to LambdaCDM do not necessarily have the same effects that they would if you realize them in an actual phenomenological model. That is, in a phenomenological model that would give you these naive extensions could have surprising cosmology. The parameters could act differently and be related in different ways, such as what I presented you here. And this is all. Thank you very much for your attention, and I'm happy that you paid attention here.